Sajad. Megan. King Boy. Johanna Cangelosi.
Here.
Still trying to make face connections. Elizabeth, I see you back there. Monjay. Daniel Cotter. Pauline Cruz. Dima. Alright. Daniel Duca. James Helms. Beth. Christian Mendola. Tuna Wen. Wait, right. And Vinwen. Charles Oaks. Sarah Parker. Josh Person. Emily Phillips. Tyler Preston. Rachel Rodriguez. Samuel Rothie. I'm working on it. Daniel Smith. All right. And Kristen Tran. All right. A bunch of people listen here today. Now, you know that my policy, according to my syllabus, is, and your last name is? Connor. Okay. Is that if I have more than 3 people missing, I don't have to post a recording of the lecture. That could become problematic. Moral of this story is, talk to your friends, make sure they show to class. This will be your one and only forgiveness day. So make them show up. What's your last name?
Hodge.
Oh yeah, I saw you and I
Okay.
did actually call your name. I said Laura Hodge. Oh yeah, you're here.
Oh, sorry.
You're in a different place.
I
I hope it was a good place.
I was filling up my laptop.
I hope it's a good and happy place to get ready. All right, so let's get working on this. Now, there are some people that are probably thinking, oh, I'll just take the quiz that's due today. Right now, it actually shuts it down and it doesn't take it if you do it late. So, yeah. Let's go ahead and get this going here. All right, hopefully you can see my screen, yes? All right, let's go ahead and move ahead here. Last time we talked about hypotheses and the scientific method, and today we're going to move forward into the PSS chapter. And some of these things we've already done, which is why your reading for today didn't include the first section unless you wanted it to, unless you wanted to read through that. We talked about making measurements last time, and we said that when we make a measurement, let me get my date here, that we would need to take into account the N, the M and its value, the uncertainty and its value. What is N for this measurement? 10. What's M for this measurement? 0. Because M's are marks that are there. So this, if it were right on this number, M would be 0. This would be M equals 1. So at this point, we're not yet to the first mark. Then we need to read between the lines. And what do you think this is? It has to be a number between 0 and 9. Yeah, so you find your halfway point looks like maybe 7 or 8. We may not agree on that, and that's okay. But you have to, this number is always going to be a number between 0 and 9. This number, there's no guarantees on that because it depends on how many marks there are. Now we need to figure out what the value is. What was the formula we used to find the value of the mark? Range over spaces.
So if I look at a range of numbers, there are 2 spaces here. So my range was 10 minus 5, 2 spaces. Apparently each one of those is worth 2.5. It's the value of each of those tick marks. And so if you check it, at this stage, you should be able to check it. This is 10. This should be 12.515. Apparently, we calculated it correctly. It's not a bad idea to check your calculation. Are you with me? Awesome. All right, so our last thing is we need to figure out what the value of these little imaginary steps were, and how do I calculate that? It's big M divided by 10, because in our heads, we took this whole space that was worth 1 marked value and divvied it up into 10 smaller steps. So it makes sense that it's going to be whatever that marking was divided into 10 smaller subdivisions. So 2.5 over 10, or 0.25. Now, here's an important idea. Because U has 2 decimal places, any measurement with this device must have 2 decimal places. Even if they're zeros. Zeros could be measured zeros. If it were pointing right at this number 10, then it would be 10.00. Because this measurement allows us the precision of 2 decimal places. So in this case, I've got 10 and 0. 7 times 0.25 is 1.75. So apparently 11.75. Plus or minus what? 0.25. And our units here we were told were amps. And so that is our total measurement. And typically, just because of how the time works out, I have students make a measurement on this before we talk about it. Because by the time we've talked about it, people realize that the number they came up with was not even close unless they followed the procedure. Yes. Just like if the analogy for this is that if I were to dump a handful of coins on the table, I'd have to count how many coins and consider how much each was worth. So that's what I'm doing here. It's the uncertain estimate part. Well, remember, we took this whole space of M and divided it into 10 smaller subdivisions, right? So M divided by 10 would give us the value of each of those subdivisions. Yeah. Absolutely, because this one you're going to be using every day you're in lab and every lab after this class. So it's an important idea. So last time we talked about making measurements. Today we're going to look at some of the units of measurement. One of the things that's really important for you to do, and many students don't consider it important until it comes back and bites them in the butt, and then it develops relevance. It's really important that you understand the correlation between what the unit is and what it represents. Mass is going to be either ounces if you're talking about the US system, or it's going to be in grams. Because if you have a formula that says you're going to need to know the mass, and then you have a word problem that gives you information about ounces, then you should be making the correlation that that ounces is the mass that you're going to be using in your calculation. So you should be familiar with what type of unit. This is the type of unit, and these are some common units. Our country is the only one in the world that still uses the imperial system. Theoretically, in 1974, we converted to the metric system, but it's too expensive to make all of the equipment to turn that over to metric. And so what happens is that the law says that if you create a new factory, you have to use all metric. If you still have old equipment, you can continue to use it until it expires. And then that's why you have a car that could be built in the US that has both SAE and metric bolts in it. It's because it depends on which factory it was built in. So the rest of the world has moved on to metric because it's more convenient. As you can see, there's not a common number of things that move to the next larger unit. And that's a little bit annoying. So the rest of the world works with things that are always multiples of 10s. Because we still use USCS, you have to know them both. So you should know common units in the USCS. You need to know what ounces are and pounds and T. What's T stand for? A ton. And you should know this. And you should know that the base unit for mass in the metric system is grams. That doesn't mean that they can't work with things like, what's your last name? Person. All right. Thank you. That doesn't mean that they can't do things like kilograms or milligrams or megagrams. Those are all relatives of the gram. But the base unit for the metric system is grams, and you should know that. Now, this is what I call a critical link. If I want to go from the US system to the metric system, I need to have some correlation. There are a lot of different approximations. We don't deal with approximations in science because that tends to cause us problems. We need to know exact definitions. And so this is an exact definition. Your last name? Phillips. You need to know the exact definition. It's going to limit your answer if you don't. It's going to cause problems if you don't. The space shuttle, the Challenger that exploded, was a problem where somebody assumed that their number was better than it really was. It is a thing, and it's an important thing. There was a bridge in St. Petersburg that was built to connect I-275 from the Palmetto side to the St. Petersburg side. And when they came to join the spans, because they have to build it from both sides, they were off by over 3 yards. And it was because somebody assumed a number that was better than it really was. So these are multi-billion dollar errors aside from the loss of life. So that's why we really work with good numbers. At a minimum, if you learn a constant, in this class, I'm always going to give you at least 4 digits of that constant, because 4 digits will take care of most any situation you're going to work with. This number talks about a unit that you have all seen at some point in your life. Back in the old days, they used to call this an AMU. What does AMU stand for? In biology, they call it a Dalton. I know you've heard it. Atomic mass unit. They decided back in the day that that was just way too long of an abbreviation. So now, just in the past few years, they've decided that instead of calling it either an AMU or a Dalton, we're going to go with one simple abbreviation, because having multiple names for the same unit is stupid. So coming up with one, now they call it the unified mass unit, because it's unifying all the different things. Big picture is you need to know what it is. Notice that it's a really tiny quantity because it takes a whole lot of them to make a single gram. To give you a sense of scale, the mass of a paperclip is about 1 gram. So you can see that the AMU, or the unified mass unit, is a teeny tiny unit. So you should know what mass is. If you're going to measure mass, you're going to use a balance. This is not called a scale. It's a balance. You are working with a standard mass, and you're putting your sample here. And so a balance is really a comparative device, because you're comparing what your sample is like to a known standard quantity. And so you're going to be working with this in the second lab. This is different from your bathroom scale. Masses are not the same thing as weights. They're related, but they're not the same thing. And we'll talk about that in just a few minutes here. Oops. Volume. We use the word mass incorrectly in common language. People say, oh, it was massive, and they don't really mean that. What they mean is that that object was voluminous. It took up a large volume. So volume is the amount of space that something occupies. Common units in the USCS system, if we talk about teaspoons and tablespoons and fluid ounces and cups and pints and quarts and gallons. Metric system, the liter is the base unit. Now you'll notice that I abbreviated the liter. Many authors have started to do that because it's very hard to determine the difference between this lowercase l and the number 1. It looks almost identical. And so because people couldn't tell the difference between the number and the unit, most authors have started to record liters as an uppercase L. Honestly, it doesn't matter if you're writing it by hand. Just give yourself a little bit of a space before you put the unit in, and then it'll be obvious to you. But that's why, in case you ever wondered. Now, in the international system, the base unit for the metric system is the cubic meter, because it turns out that volume can be measured in 2 different ways. We can measure it directly if we have something that is a liquid, for example, and your graduated cylinder is what we typically are going to use in lab to measure volumes directly. At home, you have teaspoons and cooking spoons and measuring cups. And so at home, you are measuring direct volume measurements. However, because volume for a regularly shaped object, meaning that it's a perfect square, a perfect rectangle, a perfect cone, whatever, there's formulas for that. And so one of the things you're going to do in your second lab is to determine the volume of a cylinder. And since a cylinder is a regular object, meaning has a regular mathematically described shape, then you can calculate it using dimensional or length information. And so that's why you can end up with things like a cubic centimeter. That if I have a cube that is 1 centimeter on each side and 1 centimeter tall, then I'm going to have a length times width times height cubic centimeter. This is no longer considered, or people talk about cubic centimeters. They used to say 1 cc. You've probably seen that. This is now considered obsolete. They made every hospital change their descriptions because of confusion. Now they have to talk about milliliters. So 1 cubic centimeter, this is the official dimensional way of describing that, is the equivalent of 1 milliliter. It's the same thing. One's measured directly, one's measured using dimensions. So the SI unit, the international unit, describes it in cubic meters. SI was developed for trade purposes. The idea is that most things that we're buying or selling internationally are going to be large enough that measuring it in meters is a reasonable choice. Most quantities that we buy and sell are large enough where a kilogram is a reasonable choice. And so in the SI system, for example, the SI unit for mass is a kilogram. So again, that was chosen for trade purposes. I'm not going to lie, in this class, I don't really care about the SI so much, but in your next class, you're going to use it because they've decided that they're going to base any new unit definition on existing SI units. And again, that was determined for trade purposes. So you should know the common units of volume in both the USCS system. You should know that the liter is the base unit in the metric system, and the critical links here you should know. Now, one of the things you'll notice in your reference pack that I gave you, the first week pack, it's also in the course pack that I gave you, is there's a few appendix pages. One of them that I gave you in your handout was the periodic table. This third page here, these are all the things you're going to have to memorize before the first test, in addition to the first 40 elements. So if you're somebody that needs time on memorization, I tell you right now, you need to look at this. Going to be elements 1 through 40. And you know that you have a quiz next week on the first 20 of them. So this is what you need to be sort of focusing on. If you're a note card kind of person, you need to do this. And just to sort of put this into perspective, when you take an exam with me, the first few minutes, you're going to be working on your memory section, where I'm going to select some of these to have you fill in. After you have turned in the first portion of your test, now it counts 10 points towards the total. After you've turned in the first portion, everybody's turned that in, then I'll give you this page so that you can use the correct values when you're setting up problems. So there are just some things that you should know. Jay Leno, and I know that they do it in at least one other talk show, had this thing called jaywalking, where he would go around and ask people things that people work with in a common, in common life. How many inches are in a foot? Just things that theoretically you should know if you're an educated person. And it was shocking how many people knew very, very little about the things they work with every day. It is an expectation, especially if you're in the sciences, that you should know some of the fundamental measurements. I can assure you that astronauts are not carrying lots of books on the space shuttle. They know a lot of information because they need to deal with the possibility that they can't even Google it, gasp. They may not even have communications. So there's some things they just have to know by the seat of the pants. You're not going to find an engineer who has to stop and look up how many inches are in a foot. I can guarantee that. Not one that has a job, and not one that can pass the certification exams. So it's one of those things that we need to get you a fundamental level of literacy in science. So we talked a little bit about the fact that mass and weight are not the same thing. Weight is actually a force that gravity exerts on mass. The weight is the gravitational acceleration times mass. Which means that the units of weight appear to be the same, but they really aren't. If you were taking physics, you would find that in physics, they would talk about grams of force versus grams of mass. Because a gram of force is not equivalent numerically. This is 9.8 meters per second squared. So numerically, a gram of weight is not even the same value as a gram of mass. Now, we're going to help you out here. In this class, we're only ever going to look at this one. We're only going to be working with masses because in our lab, we only work with balances. If I want to measure weight, that's what a scale does. A scale is measuring, honestly, how much force it takes to compress a spring a certain distance. And so you're not comparing one mass to another, which means that if the scale is broken, you would have no way of knowing it because you're not comparing it to a standard. I had a bathroom scale that I loved. It told me, I had it for 30 years. It told me I weighed 120 pounds. I've weighed 120 pounds since I was like 15. And I love that thing. Every single day it told me the same number. It was just wrong. So that's the thing about a balance. A balance is going to hold you honestly to a comparison between what we know is true and what your number is. So we don't work with weights, but I mention this because that's the difference between them. Which brings us to time. Most of us know what time is. you may notice that it's the same units on both sides. The difference between the metric and the US side is how they abbreviate the unit. Notice that on the US side, I shouldn't have that period there, that's a habit. On the US side, they are abbreviating a word and therefore they have a period in the unit. There are no periods in the units on the metric side. They thought that was unnecessary. Notice that they don't even abbreviate them identically. An H is the same thing as an hour. It's just that they simplified it in the metric system. So you should know both. Why is the year 365.25 days? Because of leap year. This is actually the definition of a solar year. Because most of us don't want to have to count each year in terms of a quarter of a day, they just decide that every fourth year we'll add the extra full day in there. But this is the definition of a solar year, and that's the one we work with. Distance, length. What kind of things do we use to measure distance or length? Or what kind of equipment, I should say. Yeah, you're going to use things like a ruler or a caliper if you're talking about very small quantities. Yardstick, meter stick, whatever. US side of things, you should know the first three common units. Now, most of you actually already know some of these. One thing that will help as you're working with these, as we will be in chapter 2 and 3, is think about the way that you learned it back when you were in like 3rd grade, because they started making you learn this thing according to the state standards about 3rd grade. What's bigger than an inch? What's bigger than a foot? Yard. What's bigger than a yard? Next one up is a mile. You know that. Then go back and put in the details. When you're learning it, because you learn it from small to large, process the information from small to large, and it's going to be a lot easier for you. Now, I always have somebody that says, well, what if I know that there's 5280 feet in a mile? Knock yourself out. Use that. If what you say is true, I'm all over it. If what you say is an approximation, not so much. 2.2 kilograms is not the same thing as a pound. 453.6, again, 4 digits, is grams is a pound. So approximations are not good. Absolute definitions. Turns out that the exact definition, for what I call the critical link, between the two is 2.54 centimeters is exactly 1 inch. Don't need a critical link between USCS and metric on time because time is universal. It's just that they abbreviate it differently. So are we okay with that? Oops. So we talked about measurement last time. We said that measurement always involves some comparison. We're always going to have to estimate. Measurements always require units. Measurements are always going to have one digit that's inexact, that was estimated. And you say, well, then I'll just use an electronic balance. And there is a portion of the circuit that's called a comparator circuit that says if it's above this much, round it up to the next one. If it's not that far, then round it down. So internally, it's still making a decision. There's no such thing as an exact measurement. Big idea. Everything has some estimation, whether a piece of equipment is making that decision for you or whether you're doing it. How much it's uncertain depends on you, the observer, and the instrument that you're using. Because as you know, not every piece of equipment is marked to the same degree of precision or same exactitude. In science, anything that you measure up to and including that first estimated digit are recorded. So if it's a 0 in the use place, you still have to record the 0. This is another way of saying that the decimal places in your measurement have to equal the decimal places in your uncertainty. When it says plus or minus 0.1, that means you must have 1 decimal place in your measurement. If you aren't, then you are rounding, and that's not okay in a measurement. Measurements are as accurate as they can be, meaning that we try not to introduce any extra error. As I mentioned earlier, the reason for the N plus MM plus UU thing is because when you do have coins, you have to sort them out. If you had dollar bills that clearly have the numbers written on them, that's fine. Other than that, you have to sort them according to what they are. I've got 1, 2 dimes that are worth 10 cents. I've got 1, 2, 3 quarters that are worth 25 cents. I've got 1, 2, 3, 4 pennies that are worth 1 cent. I've got 1 50-cent piece that you may never have seen in your life. 1, 2, and 3 nickels are still in circulation. And so I have to take into account how many and their value. And it's not usually written right on it. So you had to figure that out. So in measurement, we're doing exactly the same thing. We're taking into account how many and what they're worth and adding up all of those. It's just that we're only ever going to really need 3 things. As we mentioned last time, the values of the markings on a device change with the equipment, but not with your sample. Nobody comes in and scrapes the paint off your graduated cylinder between your first and second trial. The paint is there, and that's set now for that piece of equipment. We said we could figure out the values, and the values are the ones that I capitalize, in this case by taking the range and dividing by the spaces, and we looked at that. But we said we will always read between the lines, and that's where our little u's come from. And the value of that estimated value is always what big M divided by 10. So if I'm looking at this device and what I'm measuring here is something that ends up here, that's a 7 and that's an 8. Then on this device, what's N? What's M? What's U? Maybe 3 or 4. Yeah. And so the first thing we record is what number are we seeing? M is how many marks? The first mark is 0, 1 passed is 1, etc., etc. Last one, we said that if we could sort of in our head, and I'm just zooming in so that I can mark it a little more precisely here. I try to find in my head where the halfway point is, and I know that that's always going to be 5, because I know this last digit is always going to be a number between 0 and 9. So find where 5 is, and then anything else is going to be relative to that. So on that device, what's my range? Right, 8 minus 7, high minus low. And what is the number of spaces between them? 5. Again, space, 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 and space. There's 5 of them. So my range is 1. Spaces is 5. 0.2 is going to be the value of each of those markings. And again, I can always check that. 7, 0.2, 0.4, 0.6, 0.8, 8. Okay. So honestly, while you're learning, take the time to do that just to make sure that your M value works. Because if it's right, then you know automatically what the next one's going to be worth. Because it's always going to be 1/10 of that space difference, 0.02. I'm taking bets that the missing people are going to come at 1. How many people think they're going to show up at 1? because your lab lecture on Tuesday thing. I'm taking bets. All right, so let's have a look at this. 7 plus 1 times 0.2 is 0.2. Plus 3 times 0.02 is 0.06. And because this is measured, we have to record every place that we have. 7.26 plus or minus what? 0.02. And our units in a graduated cylinder are milliliters. And we already talked about that one. Let's look at this one. N plus MM plus UU. What's N for this one? It's the same device, so I already know that the values aren't going to change. But where the arrow is pointing is different now. Again, M and U's, NMs and U's can change with the sample, but big M and big U only change with the equipment. So what's M for this one? 2. And U? Find your halfway point. I think it's like 2 or 3. We may disagree. Would you agree that 4 would be a little bit higher? So try to find your halfway point and it'll give you some centering capability here. So 7 plus 0.4 plus 0.06. This one is 7.46 plus or minus 0.02. Again, graduated cylinder would be milliliters. Are you with me? Stop me before I kill again. I'm sorry? This is the last one is as we're reading between the lines. We know it's going to be a number between 0 and 9, so we find our halfway point. The end of this arrow is something below 5, but we don't, 2 or 3, probably a reasonable estimate. So this is the one that's challenging, and that's why, that would still be fine. If you said it was 8, no. Yeah, so I expect that you're going to be within, that tolerance. So notice that the big U value, this plus or minus value, honestly depends on the markings on the equipment. If I change the equipment, then it could be a different precision. The precision means how much of a window of wiggle room I have, that your answers should be consistent within that range of numbers. And if they're not, you're not using the equipment properly. So we always read between the lines for the best estimate. Ideally, when we're choosing a device, we would like to choose a device that measures to a precision that's about 1/100th at least of the object. What do I mean by that? If I'm measuring something that's 4 centimeters, then I need at least something that's plus or minus 0.04 to have any sense that the number that I measured is reasonable. This is the analogy. If I need to measure the width of a hair, I'm not going to use a yardstick because the gaps between the markings on a yardstick are too large to be useful for me. The gaps between are what's determining this. So maybe I use a caliper that can read something to the nearest that many centimeters. So at least 100 times, ideally 1,000 times smaller. And at some point, there's a law of diminishing returns. In general, if you can get 4 digits out of any measurement, you're gold. So all measurements involve an estimate. That's the U part. Therefore, they always have error. We always record all the digits, including that estimated digit, because it was still a measured digit. And anything that we measure, we're going to call a significant digit or a significant figure. I'll probably abbreviated SF on your lab reports or call it a sig fig. But what we're saying is that that was a measurement that we trust. And how many sig figs you get in a measurement are limited by the equipment. I gave you an example here of 2 thermometers. Looking at this one, based on the range of the spaces, I've got a range of 30 minus 20. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spaces between. Which means my uncertainty on this device is 1/10. With this device, my range is 22 minus 21. Spaces between still, in this case, is 10. There's not always 10 spaces between lines on devices, so you always have to check. So I have 1/10. So our uncertainty this time is 0.01. So both of these devices are measuring a number that's actually very similar. It's just that one of them reads to another decimal place than the first. So if I were making a measurement with this one, 20 plus how many marks past 20? I'm reading what my thermometer says. 1. And we know that that's worth 1. And how many uncertain measurements? If I find my halfway point is roughly 5, what do you think that one is? Maybe 3? Again, this number has to be between 0 and 9. And I know that it's worth 0.1. So this first measurement gives me 21.3 plus or minus 0.1. Looking at the second device, my N is what? 21, because N is the printed number that I've passed. How many marks past 21? 3. And I know they're worth 0.1. And what's my U value for this? 1 or 2? I think it looks like maybe 2 that are worth 0.01. This one is 21.32 plus or minus 0.01. They're both reading essentially the same temperature, but because the markings are different, you get a different number of significant figures. Because this one allows us an extra place, it gives us an extra significant place. All right, so significant figures is what they introduced in the second section here. And if you have measured it, then there's not a question at all. 1/10 of the smallest marking, whatever you measured is significant. And that's what the whole section 1 was trying to get you to understand, that you have to show every digit, even if it's a 0. And if you measured it, then it is significant. The rest of these rules are for numbers that you did not measure personally, or that you were not given any information about the precision of the equipment used to make that measurement. So these rules are going to give us a conservative estimate of significance. And we want to be conservative, meaning we don't want to assume an answer that's better than it really is. So the first rule says, if it's an exact number, it has infinite sig figs. There aren't that many things that are exact numbers, by the way. However, if it's a definition, that would be an exact number. 12 inches equals 1 foot. It doesn't matter how many decimal zeros I put after the 12. I can have an infinite number of places of zeros, and that would still equal exactly 1 foot. So because this is an exact definition, then it can have infinite places. They just don't bother to show them all. Clearly, you can't show infinity, right? So if it's an exact definition, then it has infinite sig figs. If it is an estimate, then it has limited sig figs. So it has to be exact. That's why we work with critical links in this class, because we don't want to introduce any more error than we have to. If it is a number that can't be subdivided and have any sense, the average family has 2.5 children. Is there any family in America that has 0.5 of a child? No, it's not possible to talk about a child in halvesies. They either are or they aren't. And so in that situation, the number of children in America has to be to the ones place with infinite zeros afterwards. So if you are talking about counting in the ones place, now if you're talking about a larger number, 200 is an estimate. You know, there's 20 people in this class. I haven't counted. If I took the time to count to a one person, then that would be then an exact number. So if it's been counted to the ones place and it's something that can't be subdivided, then that would be considered an exact number. And so there aren't that many situations where that's the case. So our issue is what happens with all the other numbers. Somebody gives us a number and you didn't do the measurement. You don't know the precision of the device. You just have to make a best conservative estimate as to how good the number is. Well, the first rule says that non-zero digits are significant. That they probably didn't tell you the number 3 unless they meant the number 3. Zeros that are between significant figure or digits, we call these captive zeros. And the number 101.50. This is a captive digit. If this is significant and this is significant, then this must also be significant. So captive zeros are always significant. Zeros that are at the left of the first non-zero digit. 00105. I could write the number 105 that way. I could write it this way. It wouldn't change the magnitude of it. That I know that these are significant, and these in front of it on the left side are called leading zeros, and they are losers. Ever. If they're honestly, they're just trying to add numbers and they're just trying to line it up so that they're keeping track of where their places are. Sometimes the output of a digital measurement device will show zeros until you have something in that place. Yes. Mm-hmm. Mm-hmm. I can guarantee that's not true. If you can find the problem, then let me know. We will talk about something else because you might have been missing something. Yeah, so again, if you can find it, I will happily look at it. Zeros that are at the right of the non-zero digits. So these are the only ones that are questionable. If it contains a decimal point, then it is significant. But if there's no decimal anywhere in the number, then it is not. Absolutely. When I'm looking at this number, so it's the right-hand side, what we call the trailing zeros, that are the problem. These are the only ones that are questionable. When I look at this number is a trailing zero. It's at the far right side, so it's trailing. But there's a decimal point here, and so it counts. Whereas if I had the number 1050, the non-zeros count, the captive zero counts, the trailing zero does not count because there's no decimal in the number. Doesn't matter where the decimal is. If there's no decimal anywhere, then it just doesn't count. It could have been a rounded number, and we just can't assume that it's good. Now, that doesn't mean that this is the same thing as 105. What we're saying is that we just don't trust whatever this digit to have been a measured value. We still need it as a placeholder to tell us how large the number is, but we can't trust that it was a measured digit. So let's look at some examples here. We know that the non-zeros count. What kind of zero is this one? He's captive, and he's going to count, therefore, 4 sig figs. We know the non-zero counts. Because these are at the right side, they are both trailing zeros. Do they count? When do the trailings count? There's a decimal. Doesn't matter where the decimal is. If there's a decimal anywhere in the number, then those two count. I know the non-zero works. What kind of zeros are these? Trailing. Do they count? No. There's no decimal point. The decimal points out their significance. There's no decimal, 1 sig fig. It means that for placeholder purposes, we have these zeros so that you know that it's the number 100 as opposed to 1. But we don't know if this was rounded from 80 up or whether it was 140 down. We don't know anything about that number, so we can't trust anything other than this first one. If they're at the left, they are losers. Leading left losers. So those are placeholders. You can write as many at the left as you want. It's still not going to make it significant. The reason we use those placeholders is to give a sense of magnitude. You know, where is that significant digit? We know the 5s count. What kind of zeros are these? They're captive because they're between the 5s, and therefore they're going to count. What kind of zero is this? Trailing. Does it count? Yes, because there's a decimal point somewhere in that number. 1, 2, 3, 4, 5 sig figs. Most people get through this section fairly reasonably once you learn the rule about the decimal point. The trailing zeros are the ones that get you until you finally get the idea that it's all about the decimal point. It doesn't matter where the decimal is. Trailing means that it's at the far right of everything else. Leading means it's at the left of everything else, and leadings will never be significant. So leadings are left and they are losers. The ones at the right are the only ones that are questionable, and you just have to look for a decimal point.
You're referring to the decimal point.
I'm talking, no, with the leadings, it doesn't matter if there's a decimal. It just, if it's at the left side, it's never going to count. It's just there to give you a sense of magnitude. Which brings us to the concept of rounding. This author, as many do, they're trying to be fair about it in terms of rounding, but nobody who actually works in science deals with the rule that they gave you in the textbook in general. Look at the numbers that you're trying to round. what we know is that in our calculation, we're entitled to 3 sig figs. So I'm going to find the first 3 digits that are significant. And the first digit that is questionable is going to be what I call our deciding digit. Only the first one will help us to decide. So the digit that's to the right of the place you're rounding, that's what I call our deciding digit. Makes that choice for us. If this number is less than 5, round down. I hate that phrase because you're not rounding down, you're just holding the last digit. Yeah, they might call it rounding down, but it really means don't change it. That means that this number, 1.45 times 10 to the first, is now properly rounded. I just don't change this one because the 4 doesn't give me a reason to change it. I get 3 digits, 1, 2, 3, which means that my deciding digit in this case is an 8. Since my deciding digit is greater than or equal to 5, I'm going to round up. And that really does mean what it means. I'm going to add 1 to that last digit, 1.51 times 10 to the minus 3. Now you will notice that automatically I've been ignoring this part, which is an important idea. If you have a number in scientific notation, the sig figs are in your coefficients. Not in your 10 to the term. So that's why I didn't care about this. This gives us a sense of magnitude, but this is where the sig figs are located. This is telling us how many placeholder zeros we have and where they are. So I've got 1, 2, 3 digits, which makes 5 my deciding digit. What should I do? Round the last one up, 1.46 times 10 to the second. 1, 2, 3 digits. My deciding is a 3. What should I do? Hold. 1.50 times 10 to the minus 4. There are some books that say, and this one probably does, if the deciding digit is even and then odd, then you do one thing. They're trying to be fair about it in terms of half the time you'll round up and half the time you'll round down if you had a 5. Nobody does that. Not one person in science does that. So we're going to go with the 5s. 5s round up. Go ahead and take 5 because you're going to need it. You see that it has the course home that has your assignments, and your assignments show up in a calendar. It has a little plus sign for everything that's coming up. So schedule assignments. I don't schedule it. You have a calendar. I know it looks different on your side. Let me see if it'll. Yeah, I have to sign in again to time me out. There you go. So you have a calendar here. The calendar will show it to you in an uglier calendar view. Mine actually shows exactly what it is so that I can make changes. You see a plus mark, and if you click on the plus, then it will come up with the name of the assignment and all of that. The list view, you see a list like this. And so the first homework assignment is Chapter 1 and PSS. And you'll see that I moved it for your class to be due on the 16th. Theoretically, you could get it done earlier, but I moved it to that date. So you have a calendar. It looks a little bit different than me, but you might find the list view. It gives you the choice. It shows a little icon of like a task list, and then it shows you the icon of a calendar. And so you have the option of both. And many students prefer this one, it's a personal choice. You also have in your course the eText link. So if you go to eText, it's going to open a new window, and it is slow. As you can see, it takes about 10-15 seconds for it to load, and people think it's not loading and they give up on it and they close the window. It just takes a bit. There it goes. Now, when you come into this, it has Chapter 1, Prerequisite Science Skills, Chapter 2. You can click here. You can go to a specific section if you want. We were doing 3 through 6 for today. Click on that link, and it will take you into that section. Yeah, most students do because it's a weird chapter name. And so it talks about the rules. One thing that is nice about the eText as opposed to the hard copy of the text is they have a couple video examples that show you how to do one thing to another. So the eText does have a couple of advantages to the other one. At the bottom of the page, once you finish it, then you can move on to the next section. And it does remember where you were last. So if you go back to your table of contents, it says, again, it's slow loading, and I do apologize for that. Continue reading. It remembers that you were last on this section. So then it'll take you back to where it was. Now, what many students don't know is that you can make notes to yourself here in this. You have the option, when you print, you can only print a small amount at a time. You can bookmark, you can highlight stuff, and then make a note to yourself about it. And then when you go back to your textbook, I'm going to make a note here. Testing. Oops. One, two, three. And I'm going to save that note. If I go back to my table of contents, I have not only the contents, but also my notebook. If I go to my notebook, oh, really? Because as a teacher, it does some different things than it does to me. Darn it. Try it again. Wait a minute. Come back to the section. It should have, where was I? Yeah. You should be able to pull this up. Where is it? Oh, yeah. So it's showing wherever you highlighted anything you wrote to yourself. I can actually share that with you as an instructor. So if I thought there was something super spectacular or there's a typo and somebody tells me about it, I can highlight it, share it, and then when you open your notebooks, you'll see my highlighted section with my note about it. So that's kind of a nice feature. And so you can edit it and discard it if you like, but that is sort of a helpful feature for people that are used to writing in their text and that sort of thing. It is available. Just a matter of interest. Notes, there it is. Okay. I was just looking in the wrong place for it because they've moved this around a little bit. If you come up here to your menu, there's the contents, then there's your notes. And if you click on this, it'll take you to the specific area where you wrote it. So if you've never seen that before, now you have. Can't say that anymore. So one of the things that we can do in Pearson, it's one of the reasons that I choose this, is because Pearson has this really nifty feature called Learning Catalytics. What I'm going to do is I'm going to release control of your screens so that you can log into Pearson. Everybody's logging into Pearson. Everybody except you, that is.
I see pluses.
Mhm.
So we don't have anything to, as far as Pearson's concerned, until the 16th.
That's right. Although I would get moving on it.
Right.
I just wanted to give people a little bit of wiggle room there. All right. Now, if you are in Pearson and you look around here, I'm going to stalk somebody here. You can see, Joshua, that I'm on your screen. I'm about to share what you're doing here. One would think, be a minute. Try one more thing here. One more time. I'll be back to you, Josh. Trying to find your screen here. There we go. So everybody should see his screen at the moment, yes? So this is what you guys see. You see the list view. It can also be a calendar. If you go to the calendar and you click on the plus sign, then it expands out to what it is. What you may or may not have noticed is that it has in here the average 30 minutes. What that is based on their national average of every student who's ever worked those problems, that's the average amount of time it takes. I do that so that you can allot your time or manage your time a little bit better. Many students get it done earlier. If you have not prepared or done the readings or reviewed, then it might take you longer. Most students don't need that full time, and depending on the topic, it may take you more. So this is just an average, and I do that sort of as a courtesy to you. For whatever reason, it shows me how much time it should take, but it doesn't show you. So I've named your assignments that way. Other things that you have here. So if you don't like the calendar, by all means, go to the list view. It will also do that, and it will show you the dates that are coming up. Other things that you have here are your e-text. I'm not going to look at your scores because that's your business. But there's something down here on the course home. Where is it? This is bizarre. Just a funsie. I'm going to reload the page. Because there should be a link. That's exactly what it is. Thank you for mentioning that. Once you get rid of the pop-up blocker, then reload your page if that's been happening to you. There should be something else that shows up on your course homepage, and I don't know why it is not. Assignments. Because they've moved this around a little bit. It's normally on your course home. No. How did you get access to this? Have you purchased access, or this is temporary access? Okay, because that should work here. There's something that's missing here that should be showing up. I'm going to go to the menu, see if it shows up there. Nope. How bizarre. I'm glad I'm doing that. I'm going to stop sharing here for a second. I'm going to look at my page for a second before I move forward here. I'm going to see if anybody else has it showing up on theirs, just as a matter of interest. How weird. Megan's like, wait a minute, just take control of all my stuff, man. Well, that is just odd. Well, there was something I was going to do with you that it doesn't look like I can do today, and I don't know why. Huh. All right, well, cancel that. We'll come back to that later on. Sorry. And I'll need to figure out what's going on with Pearson. But anywho, that does resolve the question about how to access your calendars and that sort of thing. So let us move forward. Because there should have been something that was there and available to you, and I don't know why it's not showing up. All right. The next set of rules are how to manage calculations in SigFigs. So what we've looked at so far is if you just have a single number, how many sig figs does it have in it? If you do a calculation, we know that the calculation is based on numbers that have some error. That's true about any number. And so how we manage the significance depends on what operation we're doing. If we are adding or subtracting, doesn't matter which, because you may remember from math, the definition of, could you put your phone away, please? Because that's seriously distracting. Adding or subtracting, the definition of subtraction means you're adding a negative number. So it really is the same operation, just as what the sign is on the number you're working with. It says, look at how many decimal places. If you add numbers, if you were doing it by hand, you would line them up according to where the decimal places are so that you could then add them. So this is sort of out of sync. 3.247. I might even put a 0 in there so that I can line it up really well with the 41.36 because I know that 0 is not going to cause me any problems. I look at this number and it has only one decimal place, 125.2. And when I sum them, yes, I can add them the way that I always have. What? 8 and anyone? 9 and there you go, just checking. It's much less fun for me to sit around and do all the work than it is for you to do some of it. Now, if I look at the assigned sig figs, by the rules, leadings are losers. Yes, 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 and yes. By the rules, all of these are non-zero, so they all count. But would you agree that they don't agree at this point? So I can't trust that place because they don't all have a digit in that place. yes, 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 and yes, but it doesn't have a digit in that place, so I can't trust that place. So the rule about addition and subtraction is all about the places. The fancy word of saying that is that the number that's least precise, meaning the number that has the fewest places, is going to dictate how much you can trust. So you're really looking at the right side of the places. And once I find a column where they don't all have a digit in that same column, then that column can't be trusted, which means this number should be then rounded. And based on his deciding digit, I should round to hold 169.8. Does that make sense? So you might find it helpful to put the X's in there just to make sure that you're tracking what's happening there. Once you get to the end of a number and there's a digit from somebody else, but there isn't for him, that means that column cannot be trusted for every digit. This is what prevents us from having the one guy that uses a micrometer to measure something, and the one guy that's like, it's about 30 feet, and then coming up with an answer that's good to as many places as the micrometer. That doesn't make sense. And so we're limiting it to our worst piece of data because that's the most we can trust. So if I'm doing the addition here, yes, they're all significant. Yes, they're all significant. Yes, they're all significant. Look at the places. They disagree in this column, so I can't trust it. They all agree in the other columns, however. 0, 1, what's that number going to be? Is it 0 because we had to carry the 1 up here? Anyone? Carry the 1. Looks like a 55.00, and I can't trust that place. So should I round up or hold? Hold to 55.0. Don't forget your units because numbers that had units should still have units. This one doesn't have a second decimal place. This one doesn't have a second place. And so even though this one does, I use his number in my calculation because he may be my deciding digit. So I need to do all the places. I just can't trust that column. So 5, 12, 12. So I can't trust him, but he's my deciding digit, so I have to use him when I'm doing my calculation. So should I round up or hold? Oh, yeah, it could be if you, oh, sure, in your math world. Yeah. That alternate math. I should round that one up. So 22.3 centimeters. This is what happens when you write and talk at the same time. So honestly, the rule makes sense if you think about what you have to do the math. You have to line it up according to places to do the addition or subtraction. And so it should make sense to you that places is what's important here. When you're doing multiplication or division, it doesn't matter where the places are. You just do the multiplication or division. They could be arranged in a column or they can be arranged side by side, and you still do the math and you get the same answer. So the rule for multiplication and division has nothing to do with places. It just says how many sig figs, wherever they are, doesn't care. So this number has 1, 2, 3 sig figs. This number has 2 sig figs. So the one that has the fewest sig figs is going to be what determines our answer. So this is the easy rule. 1, 2, 3, 4. What about that 0? Yes, because there's a decimal point. Okay, so we got 5 sig figs there. How many sig figs here? 3. The 1 and both of my trailings count because there's a decimal. So how many sig figs should I get in that answer? In case you're wondering, I just pulled some randomly out of the back of a book when I was making up my notes so that you'd see where those came from. Now, when you do the math, 66.3 divided by, oh, seriously? 3 divided by 7.5. Now, your calculator spits out all sorts of digits. That doesn't mean they're all significant. It doesn't know better. It just did the math for us. We know that that answer should be 2 sig figs. So should I round up or hold? Hold. 8.8 units are important. Since grams was being divided by milliliters, then my unit should be grams divided by milliliters. And the second one, 42.620 divided by 10.0. I could probably do that math. Get 3 sig figs here. Should I round up or hold? Hold. 4.26. And my units are going to be grams divided by milliliters. So the easy one, honestly, is multiplication and division. The more challenging one is the addition or subtracting, because you have to take the time to look at where the columns match up. That's why sometimes when you do it in your calculator, it doesn't show the columns as effectively. So I'm not going to lie, a lot of times I'll do it by hand on a piece of paper to track it. I mean, I'm better at it now because I've been doing it for a few hundred years. But back in the day, I did a lot more on paper then. Now, if I mix operations, the rules still work. I just have to find the order of operations. What is the order of operations? Some people call it PEMDAS, some people call it GEMDAS. Grouping instead of parentheses. Why grouping? Well, because anything that's in a numerator, for example, is a group. So it doesn't matter whether it's in parentheses or not. If it's the entire numerator, that would be a group. So grouping has to be accounted for first. Then what's E stand for? Exponentiation. And honestly, multiplication and division are the same things, because by definition, division means you're multiplying by an inverse. Addition and subtraction are the same thing. By definition, subtraction is adding a negative number. So grouping, exponentiation. So there is no preference between multiplication and division because they're commutative. There is no preference between addition and subtraction because they're commutative. So pick one. So I have several groups here. I have parenthetical phrases here that I have to do the math first before I can do anything else. So 300, 10, and 1. I'm sorry? Yes, numerically it comes up with 311. So let's check our sig figs. The 3 is good. What about the zeros? Nope. There's no decimal point. Which means that I have to stop here. Now, here's the thing about mixed operations. I can't just round intermediately. I'm going to have to carry these digits, but I have to make a note to myself that they're not significant. Because if I round before I'm done, then I'm going to introduce error. Because there's multiple steps in this process. If I round and then round again and then round again, I'm going to be increasing my error every time. So what I do is I want to carry 2 extra sig figs, 2 extra insignificant digits, until I get to the end. Now, I do know that I have only 1 sig fig here, but I need to carry at least 2 extra sig figs to do this. I personally just never clear anything out of my calculator. I just keep everything in my number. Do the same thing here. I got 4.2, I've got 3.55, and I've got the number 10. So mathematically, 17.75. Checking here, I get the 10th place, but I have nothing here. I have nothing here. Is this 0 significant? No, because there was no decimal in that number 10. So again, I truly only have 1 significant digit here. Stop me if you do not understand what I've just said. Which part? Are you okay with why the 0 is insignificant? Yes, because there's no decimal point in that number. Now, we said that if I come to a column where there's disagreement, I didn't have a number in either of these two. That means I can't trust that column. In this column, I had at least one of them didn't have a number, so I can't trust that column. This column I know is insignificant, so I can't trust it either. So this is my number, but I know I can't trust those 3 columns in terms of significance. But I can't round yet because I'm not done with my problem. Does that make sense? So I label them so that I'll know how many sig figs I have. Now what I have left is all multiplication and division. And those rules say it only matters number. How many sig figs are in this number? 1. I have 3 digits, but only one of them was significant. How many significant digits are in this number? And in this one? So when I get around to my final answer, the rule says I have to choose the weakest link. Since a couple of the factors have only 1 sig fig, my answer can only have 1 sig fig. I think it comes out to number 4.
Generally speaking, that would be like.
Absolutely, because these numbers were very poor. And because these numbers were poor, then our answer can't be good. If each contributor gives you garbage, then you have a large mound of garbage, but it's still garbage at the end of the day. So the whole point of sig figs is to say, how much can I trust it? And based on all these measurements, I only get 1 sig fig. That means your measurements were pretty poor. So let's see what happens here. Because it's all addition and subtraction, it's all about the places. 1.22, 0.01, and we're going to subtract 10. I know that the 10 doesn't have either of those decimal places. So when I do the math, I'm only going to be good to this place. Do you agree to that? Oh, I'm just saying that I haven't yet looked at what the numbers are. I'm just saying that this place will count. The 0 I can't trust because there's no decimal point. So maybe I don't understand your question. Oh, right, when we do the math, actually. Okay, so 1.23 minus 10, because these two are at least in agreement, gives me what, 8.77 to the 1's place, which is the only one I can trust. That's what I have. Since this is my only significant digit and this is my deciding digit, should I round up or should I hold? Round up. 10. And you say, Nance, you're showing me the 1's place. Did I imply that that was a significant place? No. What about if I'd said this? So we're starting to see the problem with placeholder zeros. I have to show the placeholder so that you know that that's the number 10 and not the number 1. But if I put a decimal in there, that implies that the trailing zeros are significant, and that may not be the case. And so the correct answer to this should be 10, but not 10 point, because the point would make the 0 also significant. Yes?
So when you round it,
Mhm.
zeros, why did you think it?
Well, because would you agree that I am adding a 1 into the 10's place? So I still have to account for the order of magnitude. I still have to tell you this is a number that's larger than 1. Thank you for asking. This time I have a mixed calculation. I have to do the grouping first. 10.22, adding to 0.02, 10.24 mathematically. And how many sig figs am I entitled to?
4.
All 4 of them. Because again, in terms of places, they agree to the last place. This one's a leading 0, but again, it's all about the places on the right side. So yes, I have 4 sig figs here. I have 4 sig figs here. And so I should end up with an answer that has 4 sig figs. Questions, concerns, or prayer requests? Yeah. Uh-huh. If the rule says find which ones are significant and then look at the columns on the right side, because that's what your precision is the places on the right side, not on the left. Good question. All right, so I'm not going to lie, that section is going to kick your butt. You're going to work on the homework, and I recommend highly that you do this as soon as possible after today, that you go through and try these, because they're not hard specifically, but there's lots of little rules. And the earlier you can iron that out, the easier it's going to be for you. So just a suggestion. The next section in your text talks about exponential numbers. Exponents are typically written as a raised number. If they only give you a number and an exponent, a raised number, then they're telling you that this number, which is called the base, and this number, which is the exponent, is telling us how many times to multiply that base. So 2 raised to the 3rd power says 2 times 2 times 2. We'd say 2 cubed. Numerically, then that's going to give us the value of 8. So the exponent tells us how many times to multiply. This is the part that bothers students. Negative exponents mean that the base is inverted. When I see this means 1 over 2 times 1 over 2 times 1 over 2. So a negative exponent means that number is going to get smaller. And a positive exponent means that number is going to get bigger in the process, which is 1 over 8. So when you're looking at numbers that have an exponent, a negative exponent is a small value. The larger the exponent, the more of an effect it's going to have. So a negative 5 would be a lot smaller than a negative 3. Are you with me? Now, what bothers many students is this situation. If it's neither positive nor negative, if it's a 0, whatever it is, whatever the base is, that base raised to 0 is always by definition 1. So 2 to the 0 is 1, 3 to the 0 is 1. It means we're not using that number at all, because it still has a meaning. Sometimes that's really what you mean, that you're multiplying by 1. You may remember from your math days that when you multiply numbers that are the same base, and you're multiplying, you're adding their exponents. Positive numbers should get more positive. But if one of those positive and one's negative, you'd still add the exponents. It's just that it's going to give you a negative or a smaller number now. So if I were expressing this, my base is 10. What's my exponent? 4. If the only number I have is in the denominator, what does that mean about my exponent? Then it's a negative value. And 1, 2, 3, 4. Would you agree that would be the same thing as 1/10 to the 4th power? We just don't usually write it this way because it's tedious. So instead of writing the inverse, we put the negative sign there and it saves us some hassle. Now, scientific notation, which you've looked at since like 5th grade, is all about exponential numbers. In scientific notation, the base is always 10. And we have some number that's our coefficient. And you'll notice that I wrote the word coefficient sort of weirdly. I put a decimal after the first digit to remind you that in scientific notation, the decimal point is always after the first digit. Always, always, always. If it's not after the first digit, it's not correctly written in scientific notation. Engineering notation gives you 2 digits in a decimal. And I have no idea why they do that, but they do. Your calculator may have both on it, so make sure that you're using the proper notation, and we'll talk about that in just a second. As we mentioned earlier, the coefficient is the significant part of it. This is just telling us the number of placeholders. Because remember, powers of 10 are where the places are in a number, a decimal number. So this gives us a sense of magnitude. It tells us whether it's a big number or small number. That's what magnitude means. If it's a positive exponent, is it a big number or a small number? Big. Positive is usually bigger than bank account that's positive is bigger than one that's negative. So if we're writing a number in scientific notation, we know it's going to be based on 10. See what I did there? Based. I kill me. And we need to make sure that we write any significant digit as the coefficient. How many sig figs do I have in this first number? Just 1. So my coefficient is 1 with a decimal after it, because proper scientific notation always shows the decimal point. Times 10 raised to the, and this time I'm telling how many placeholders there are. According to this, the place for the decimal is here. If I have moved it all the way over here, I've moved it 1, 2, 3, 4 times. Would you agree that that number is a big number? Then it's a positive 4. So many of you learn that if I have to move it to the left, it's positive. I don't even worry with those rules because that's useless, because you're going to move it the wrong direction 50% of the time because you're going to not remember what the rule is. Look at the number. Is this a big number? Yes. This number is greater than 1. That means it's got to be a positive exponent. Has to be. This number is greater than 1. It's going to have a positive exponent. This number is a big number. These, not so much. I know this one's going to have a negative exponent and a negative exponent. When you look at a number, that's what you need to be seeing. How many sig figs are in this number? 4. We've got the non-zeros, the captive, and the trailing because there's a decimal. So all of them show up in my coefficient. Did I have to move the decimal any places? That's why the 10 to the 0 exists. So I'm multiplying by 1. It's essentially still the number 2.050. And you don't have to show the positives. In fact, it's not correct to show the positive. How many sig figs are in this one? 4. 1, 2, 3, 4, and this one's trailing, but there's no decimal. So I know that it's going to be the 4 digits that are significant. I know I'm not going to show the positive here. In standard notation, there would probably be a comma in there somewhere. And in standard notation, I would know that this is the place for the decimal. How many times did I have to move it? 1, 2, 3, 4 to get the decimal between the 2 and the 3. So find where the decimal place is. Since there's no point, we just have to point out where the place is. 1, 2, 3, 4. Leading, leading, leading. non-zeros, and captive. What about the 0? Yes, it's trailing and there's a decimal somewhere. Doesn't matter where it is. Writing my coefficient, 3050 or 3050 are the ones I'm going to include, and the decimal has to be after the first one. Times 10 raised to some negative exponent, and I'm going to have to write that. Again, find your decimal place. I had to move it 1, 2, 3 times. So that's 10 to the minus 3. Again, it's a small number, so I knew it was a minus exponent. How many sig figs are there in the last example? 3. So I'm going to write those 3 digits. Leadings or losers? Yes, yes, and yes. And I know my decimal has to go after the first one. How many times did I move the decimal point? 2. And it's a small number, so it's a negative exponent. So you don't have to remember whether you're moving it left or right. You just need to know if the number is big or small. Now, yeah. I'm sorry? The 10,000? Okay, what was the first part of your question? Yes, yes, you do. For proper scientific notation, there's always a decimal point after. Well, no, because that would imply another significant digit. But proper scientific notation should show the decimal point. And people get sloppy about it, but it really should be that way. Now, your calculator probably does scientific notation. In fact, we ask you to buy one that does. They really not put one on here. Awesome sauce. See, like I said, they just replaced all the computers and they didn't put this in here. Let me see if I got it here. I don't know if I have it on here or not. Oh, darn it. All right. Your calculator does scientific notation. I do want to take a moment and quickly introduce a concept that your calculator uses. And as soon as I can get the emulator in here, then we'll be using that so you get used to using your calculator. When you put a number in your calculator, I mean, there is a crappy little calculator in here. We'll make it scientific. 2.0 times 1,000. Okay. Oh, darn it. I mean, 2.0 times 1,000. Let's give it lots of places there. Oh, really? They really aren't going to do that for me? There you go. Your calculator uses this weird E notation. All calculators do it. Blackboard does it. Excel does it. Everybody does it except for your homework system. So you need to understand what that E means. In your calculator, notice what it's doing. It's showing you the coefficient. It's not showing you the times 10 to the part, is it? The E represents times 10 raised to the, and then they show you the exponent. So when they're using the E notation, they're giving you the coefficient, then they give you an e, and then they give you the exponent. You need to know that that e represents times 10 raised to the whatever. Everybody does this except your homework system. I've actually complained to your homework system because at this point it's becoming much more standard. If you're using Excel, it will do this. So if your calculator is on the mode, the option where it's showing you exponential numbers, and most of the time you're going to want it that way, then it's going to display it in this way, which means that if I want to enter a number in scientific notation, I need to enter my coefficient. Then I'm going to find a button on my calculator that either says EE or EXP. And then I'm going to put in my exponent. It's really important that you get to using this exponential key on your calculator. So if I had this number, I would be entering 4.00. Either your button says EE or it says EXP, depending on what calculator you have. You'd put if you have a TI 83 or 84 or any of those, you're going to put your change sign key in here and then the 2. If you're working with one of the less expensive models, then you're going to hit your plus or minus, or you're going to put the number 2 and then the plus or minus might have to happen. So which order you have to put in the sign change depends on which calculator you have. Yes. That's not the one. So it's I think it's over the number 7. Do you see in blue? Let me, because if I can see yours, then it's the same place for everybody else. Yeah, okay, it's right above the 7. See, it's yeah, you can't see what it used to be. It used to be a comma. So above the 7, there's a button, and in blue it says EE. That's the one. So you need to get comfortable using that because this is implied grouping. Then whatever the exponent was. If your exponent in this case was a -2, you'll notice there's a button that has a parenthesis and a negative sign. That's your change sign key. So there's a difference between a subtraction and the change sign key. So you need to find that button and you need to get comfortable with it because you need to be learning how to use the scientific notation in your calculator. And that's where we're going to quit for today. Don't forget to log out.